Hello PyCon 2021. My name is Josh, and today I'm going to talk about quantum computing from a Python perspective. Quantum computers aren't hypothetical, and they aren't spooky. They're available today in various forms and easily accessible via Python. Now, I'm really lucky in that quantum computing in Python is my day job. I work at Xanadu, a Canadian-based quantum computing hardware company, where I help to build open source quantum software, including the open source quantum framework PennyLane. If you want to stay in touch after this talk, I'm active on Twitter. My Twitter account is Third Quantization. Feel free to send through any questions you might have. In this talk, I want to do something a little different to most talks on quantum computing. Rather than delve deeply into what quantum computers are and how they work, let's go straight into the code and see what it looks like. So hopefully, by the end of this talk, you'll have an idea of what quantum programming means and what quantum programming looks like in Python, the current state of quantum hardware, and when it makes sense to use them. And finally, how we can train quantum hardware using the rich Python machine learning ecosystem. Firstly, what are quantum computers? Now, I know I said we would go straight into the code, but with quantum computers currently holding such a mystical aura, there is no avoiding briefly mentioning what quantum computers are. So quantum computers are programmable computers that harness subatomic particles to store data and perform computations. And I just want to emphasize that there is no one way to build a quantum computer. Quantum computers have been built using superconducting electric circuits, lasers, photonics, molecules, atoms, and various other approaches. Any subatomic system where we can control the energy and perform measurement readout is potentially suitable. Now, compared to classical computers, quantum computers are able to take advantage of quantum properties such as entanglement and superposition to allow computation in an exceptionally large computational space. And the quantum computers that are available today are near-term quantum computers, and these are very specialized devices. In particular, the near-term quantum devices that we have are small. They have a small number of qubits, which are the quantum resource equivalent to classical bits. And in addition to that, they're quite noisy. So errors tend to propagate throughout the computation. Now, there is a lot of hype and misinformation surrounding quantum computing, such as the misconception that quantum computers automatically perform parallelization, or that they enable a speed up in all cases. In fact, quantum computers are highly specialized devices and will likely not replace CPUs and GPUs anytime soon. You can almost think of near-term quantum computers as accelerators, akin to GPUs for specific tasks, rather than general-purpose computing devices. It is very difficult to harness quantum superposition and entanglement to achieve speedups for all applications. Instead, there are specific algorithms that are exceptionally hard to do classically, like factoring integers, that we can do exponentially faster on quantum devices. So almost in the way that you use GPUs today, we know that GPUs are very good for parallelizing lots of small matrix multiplications. So we harness GPUs for that specific task and continue to use CPUs for other more general tasks. So instead of focusing on superposition and entanglement, it is more useful to think of near-term quantum devices almost as black boxes. And these black boxes are very good at performing matrix multiplication in an exponentially large vector space. So given the same amount of resources we might have on a small quantum device as compared to a classical device, the size of the matrix multiplication we can perform on the quantum device is exponentially larger. However, we can't access this high dimensional vector space where this large matrix multiplication is taking place. So that's one of the drawbacks that many people aren't aware of when it comes to quantum computing. While we are performing these high dimensional matrix multiplications, the best we can do is we can sample from this high dimensional space and we can extract measurement statistics from this space. So that's what we do with these near-term quantum devices. We perform measurements and we extract classical data from the black box and essentially are sampling from these very large vector spaces. Before we move on, I just want to quickly elaborate on something I mentioned earlier about quantum computers being available now and being publicly accessible. So over the past 5 to 10 years, there's been a huge amount of progress in both academic research groups and companies in building out quantum devices. While the progress has been staggering, there's still a large amount of operational restrictions. So for instance, devices that use superconducting electric circuits for their computation require ultra-low temperatures to operate. So while it's not currently feasible to have a quantum computer installed in your home or your office, these quantum computers are available, and they're available and accessible over the internet. So anyone working on their laptop or computer or mobile phone even can submit quantum algorithms to be run on these quantum devices and have the results returned to them over the cloud. A cool side effect of this is that there's been an explosion in open source quantum software, and Python has really become the home of quantum computation in 2021. So alongside these quantum devices, open source quantum frameworks available in Python include PennyLane, Qiskit by IBM, Amazon Braket, and Google Cirq, amongst many others. Now that we know these quantum devices are accessible via Python, and that in a very abstract sense we can treat these near-term quantum devices as black box matrix multiplication machines, a new strategy starts to become clear. Let's build a quantum function in Python that does the following three things. So firstly, it accepts floating point parameters, and these can be manually inputted to the function, or they could be the output of some previous computational step. Internally, this quantum function will contain quantum instructions dependent on these input parameters that are executed on either a remote hardware device or perhaps a local simulator. And finally, this quantum function will return measurement statistics. So this quantum device will be measured, providing some insight to the probability distribution of this large vector space, and this will be returned. So crucially, this quantum function accepts floating point data and outputs floating point data. This function is completely deterministic. The output is fully determined by the input. However, internally, we're able to take advantage of this very, very large computational space accessible via these quantum devices. And finally, and this is the part I find most exciting, is that because we've chosen a function abstraction, this quantum function is fully composable within any Python pipeline. So it integrates very, very well with the very rich scientific Python ecosystem. So now let's jump into the code and see what this parameterized quantum function looks like in practice in Python. So I'm going to drop into my terminal now, and I'm going to be using the quantum framework PennyLane to demonstrate this. So to begin with, import PennyLane as QML, and we also want to import NumPy, so import NumPy as NP. So the first thing we want to do is we want to provision a quantum device. So just two things to note here. The first is that I'm provisioning a device that has 2 wires or 2 qubits. This is just the size of the device that we're creating. The other thing to note is that I'm using a default qubit, which is a built-in simulator that comes along with PennyLane, and it's useful for rapid prototyping. If you're following along and you'd like to use a real hardware device, then definitely give it a go. You just need to change this line. Instead of provisioning default qubit, provision something from IBM Q, and there's more information in the PennyLane documentation. So now we want to create our quantum function. So to do that in PennyLane, we use the qml.qnode decorator, and this essentially says the following function is a quantum function that will be executed on this particular device. And then the quantum function is just created like any other Python function. So I'll call it qfunc, and it'll take some input parameters. So within the quantum function, this is where our quantum instructions come. So I'll start off with my first quantum instruction, which is, well, not to go into too much detail, but just a rotation that's applied on the quantum device within this high-dimensional subspace. So this rotation will be dependent on the first element of my parameters, and it will be applied to the first wire, the first qubit of the quantum device. I'll do another rotation, this time using the second parameter in our params array, and applying this to another qubit. Finally, I want to apply, this is a non-parameterized quantum instruction. What it essentially does is it entangles our 2 qubits together. So I've got a couple of quantum instructions now, and what I want to do is I want to perform some measurement statistic on the quantum device to be able to extract some information as output of our quantum function. So I will return And in this particular case, I'll return the probability of the quantum device over both y's, both qubits. And there we go. That's our quantum function. So let's create some initial parameters to evaluate this quantum function with. And let's evaluate it. There you go. We've got a function that takes a NumPy array of size 2 and it outputs another array of size 4. And these are the probabilities of our qubit system, of our quantum device, after we apply these parameterized quantum instructions. Awesome. So as I mentioned, the cool thing about parameterized quantum functions is that they're composable and they're very flexible. We can include them within other scientific Python packages. So we've created a parameterized quantum function here. Let's try and optimize this function or minimize it so that we're training it to output a certain value. So we can use SciPy for this. For those familiar with SciPy, SciPy has an optimization submodule with a minimize function. So let's import that. And before we can do anything, we need to construct our cost function. So this is we're encoding the function that we want to minimize to solve a particular problem. So let's create our cost function. This takes our parameters. And within this cost function, let's do a mix of classical processing and quantum processing. So let's take the sign, and within here, let's create another NumPy array, or 4 values. And since this NumPy array has 4 values, and the output of our quantum function also has 4 values, we can take the dot product between these two. So let's reevaluate our quantum function with the cost function parameters and take the dot product between that NumPy array and the output of our quantum function. And there we go. That's a classical quantum cost function in that it involves a mix of classical processing, for instance, the sign, the dot product, and quantum processing, represented by evaluating our quantum function. So we can test out this cost function. Let's evaluate it with our initial parameters. There we go. So we evaluate it with our initial parameters and we get a scalar output of 0.81. Perfect. So we have a cost function now. It mixes classical processing and quantum processing. Let's use SciPy to minimize this cost function. So we'll use SciPy to find the value of the input parameters that result in the minimal value of the output. So we call the minimize function. We pass the function we want to minimize, as well as the initial parameters that we're starting off with in our problem. There we go. Let's see how this optimization went. Amazing. So the optimization was a success. It required 2 iterations, and I believe it required 32 evaluations of the quantum function. I might have to double check with the SciPy documentation. And it's also provided us our optimal values of the parameters, which minimize that cost function. So let's test that out. So here are our minimal parameter values, and let's evaluate our cost function with those minimal values. There we go. So comparing that again to the cost function with the initial parameters, we can see that the optimized parameters result in a cost value of minus 0.84 compared to our initial value, which is 0.81. So a really, really nice result. Having composable quantum functions that can be used arbitrarily within Python is already an awesome addition. We easily provide this function to SciPy for optimization without SciPy knowing any better that it was optimizing a quantum device. I just want to quickly emphasize exactly what we did here. We used Python to train a quantum device to achieve a particular outcome by varying the parameters of this quantum device. Phrased in this way, does it sound familiar? This is exactly what we do with neural networks and machine learning, using workhorse algorithms such as gradient descent and backpropagation. In fact, Python has a rich ecosystem in machine learning frameworks, including TensorFlow, PyTorch. Can we integrate our quantum function with these machine learning frameworks and use the tools developed for deep learning to train quantum devices? We quickly run into an issue though. If we want to integrate our quantum function with machine learning frameworks, we need more information about our quantum function. We also need the gradient. And preferably, we want to be able to extract the gradient via another quantum function, since quantum gradients are quantum computations themselves and cannot be easily computed on CPUs. Luckily, there is an approach for computing quantum gradients on quantum devices. And this is the so-called parameter shift rule. which allows us to reuse the same quantum function, just evaluated at different parameter values to compute the quantum gradient. So let's have a look at that now. So again, I'm just going to create a quantum device. I'll use the local simulator with 2 wires or 2 qubits. And I'll create a slightly more complicated quantum function in this case. So you can see now that I have 3 rotation instructions on the quantum device. So 3 parameters. I have 2 entangling gates or entangling instructions. And rather than returning a measurement statistic, which is a probability, this time I'm returning an expectation value of the quantum device. So we'll create some parameters, and let's evaluate this quantum function. So you can see that it has 3 input parameters, and it outputs a scalar, 0.0289. So now let's find the derivative of this quantum function with respect to the second parameter, 0.2. So what we'll do is we'll create a shift vector, and the shift vector will result in no change to the first and the third parameter, but it will shift the second parameter by pi on 2. So what we'll do is we'll evaluate this quantum function twice. The first time with the second parameter shifted forward by pi on 2, and the second time by the second parameter shifted backwards by pi on 2. And we'll divide that by 2. And that's the gradient of the quantum function with respect to the second parameter. As a quick sanity check, let's compare this to Penny Lane's built-in gradient computation. So Penny Lane has a function q0.grad to compute the gradient of quantum functions. So in this case, this is the gradient with respect to all parameters, but we in particular calculate the gradient with respect to the second parameter, and we can see that we have a exact correspondence, which is great. So far we've seen how to construct a quantum function in Python, and we've also explored how to compute the gradient of that quantum function by evaluating that same quantum function just with shifted parameter values. So this is all we need in order to integrate our quantum function with a machine learning library to manage the optimization pipeline. So a neat feature of many machine learning packages for Python is that they enable you to explicitly provide the custom gradient of a function, allowing it to seamlessly integrate into the machine learning framework. So this is common to a lot of the frameworks. In this particular example, we'll use PyTorch. And this is just a page from the PyTorch documentation that's showing how you make something, a particular function, PyTorch compatible. And you really only need to do 2 things. You need to create a PyTorch autograd function object and define the forward pass, and this is what happens when you evaluate the function, and the backwards pass, and this is the gradient computation of your particular custom function. So let's do this now. First things first, let's import PyTorch. And we can start off by creating our PyTorch compatible quantum function. So we create a qfunc that inherits from autograd.function. And the first thing we need to do is define the forward method. And this is just a static method that takes in the environment context and the input torch parameters. So we need to save these input parameters for the backpropagation. And if you want any more details about how backpropagation works, I encourage you to read up on the PyTorch website. It provides a lot more details in that extending PyTorch page. Now the issue is that these parameters are PyTorch tensors, and our quantum function takes NumPy arrays. So what we want to do is we want to take these parameters, we want to detach them from the backpropagation, and convert them into NumPy arrays. And this gives us a form that we can use to evaluate our qfunc that we defined earlier. So we've now evaluated our qfunc, and all we need to return is we need to convert this back into a torch tensor. There we go, that's our forward method. So now let's define our backwards method. So this takes the environment context, it also takes what we call the gradient output. So backpropagation works in reverse. We're going from the output of the computation and we're going backwards through it to compute the gradient. So that's why we pass in the gradient output. So what PyTorch wants in this particular method is it wants the vector Jacobian product. And this is an array with the same shape as the input parameters. And now we can apply the parameter shift rule. So we can actually loop over every parameter to our Q node, to our quantum function. you can make a copy of the parameter array. And what we want to do is we want to shift this particular index in our parameter array by that shift value, pi on 2. And then we can evaluate the forward shift of our quantum function. Now we do something similar. We shift that same index backwards by pi. So in effect, we're now shifting backwards from the original value by pi on 2. And we evaluate the backward value. And finally, as you saw before, our gradient is simply forward, take backward, divide by 2. Now I mentioned here that we want to return the vector Jacobian product. So it's slightly more than just the gradient we want to return. We want to return the gradient multiplied by this grad output value. And this is the IDX index of our VJP vector. And that's it. We've applied the parameter shift rule in a for loop over each index in our initial parameters. So this returns the full vector Jacobian product. Now we simply want to convert it back into a tensor so that PyTorch understands it. And there we go. We've made our quantum function PyTorch compatible by defining what happens when we evaluate the quantum function for PyTorch, and also defining what the gradient of this quantum function is here. So the final step is just to create a function that is aliased to the apply method of this class, and that's it. So let's test this out now. We'll do the forward pass first. So we'll create some initial parameters. And again, we're just doing 0.1, 0.2, 0.3. We're creating a torch tensor because we need to provide parameters that PyTorch understands. And let's construct our cross function. So let's do an arbitrary mix of classical processing and quantum processing just because we can. So let's take the sign of our PyTorch compatible quantum function. And let's take the cube of that, because why not? There you go. That's our value. Oh, pretty small. Let's do a bit more. Let's compute the quantum function again and add that onto that value, this time with the square root of the initial parameters. Nice, slightly larger value. So here comes the fun part. Let's perform backpropagation through this hybrid mix of both classical processing and quantum processing. Everything seems to have worked out fine, so let's have a look. There we go, and that's our gradient. So we've incorporated our quantum function into PyTorch. We've created a PyTorch version of this quantum function that PyTorch natively understands, and not only does it natively understand, it's able to backpropagate through this entire structure. So if you have a look back at our initial slide, we've created something almost like this. Here the green are quantum functions, potentially on the same device, maybe even on different devices, and we've seamlessly integrated it with classical processing, indicated by the yellow nodes in the graph. So as you can see, we have the ability to integrate quantum computing seamlessly into Python and its myriad of deep learning frameworks. The tools that we have developed for deep learning over the past decades, we can harness to optimize and train these near-term quantum devices. Open source Python software, such as PennyLane, which we use today, and TensorFlow Quantum automate this integration, allowing for rapid prototyping. A word of caution though. I mentioned earlier that many misconceptions surround quantum computing, and especially quantum machine learning. I want to emphasize that this field is still very young, and definitely still at an exploratory stage. Replacing your neural networks with quantum functions typically won't lead to a speed up, or even better results. However, these devices have shown early promise for quantum machine learning specifically on quantum datasets. So for example, this is very common in quantum chemistry, where you might want to find the ground state energy of a molecule. Having said that, I hope that this talk has shown how easy it is to play around, have fun, and just explore what is possible with quantum computing and Python. The Python ecosystem is so rich, and with machine learning, we have seen this rich ecosystem and ability to rapidly prototype lead to new theoretical results and understanding. Perhaps the same can be true of quantum computing. I know this talk was short, but if I have whetted your appetite, please check out the following resources. So a shout out to the Unitary Fund, a non-profit organization that provides microgrants to work on open quantum software. The Quantum Open Source Foundation, similarly, helps support the development and standardization of open tools for quantum computing. If you're interested, the Quantum Open Source Foundation maintains a list of active open source quantum computing projects, so I encourage you to check them out or even contribute to a few of them. Finally, check out the Penny Lane website for further explanations and tutorials on quantum machine learning. Thank you, everyone.